Hello everybody, my name is Siavash Saki. I'm a research assistant at the Research Lab for Urban Transport at the Frankfurt University of Applied Sciences. Today I want to talk about the very first results of an ongoing research project called ClusterMobil. The topic of this presentation is clustering urban areas based on GPS trajectories and geospatial data. I hope you find it interesting and I look forward to your feedbacks and questions. As you know, identifying homogeneous regions in spatial data is very valuable for planners, scientists, and policymakers. There are actually many examples and different majors where researchers might be interested in clustering an area. Partitioning a wetland area into uniform zones based on animals and plants might be interesting for ecologists. Homogeneous clusters of a city regarding the facilities for the people who live in or visit the city might be interesting for city planners. And what you see in this figure is a manual city segmentation, which traffic planners did to understand the demand for parking space by demand groups. Manual city segmentation has been done for years, so why do we need to do it data-driven all of a sudden? Well, for starters, traditional methods of city segmentation are based either on old planning data like building permits or subjective heuristic decisions by humans. Maybe that was the only method back in the days, but more and more spatial data has been being collected for the last years. Luckily enough, these rich spatial databases are free and available to all. Alongside spatial databases, there has also been progress in machine learning, big data analytics, and computational power that let us reveal complex patterns in data. It also enables to create more complicated models, which take more criteria into account than humans can do. And lastly, by using a transferable and scalable clustering method, the comparison between different areas is more plausible. Here is an overview of the methodological approach in this research. We use the city of Hanau for our case study. Hanau is a typical city in Germany with almost 100,000 inhabitants and is located 20 kilometers east of Frankfurt am Main. I will present two different segmentation methods of Hanau city. The first one is based on geodata and the second one on GPS data. The methodological approach is the same in both, however, the implementation of each step is slightly different in each one of them. It begins with data collection. Then we generate local geographical units, or as we call them, LGUs. They are basically the spatial objects which are to be clustered. Afterward, it is feature engineering, where we define the variables based on the properties of the raw data and prepare the proper input dataset. The next step is data preprocessing, which contains data normalization and data reduction. This step reduces the chance of developing biases and deviations in our model. Then we cluster the LGUs using the k-means algorithm, and finally discuss the results. The first main challenge in this approach is dividing the city into LGUs. It contains finding the optimal number of LGUs and defining their borders. For this matter, we looked at other related works and got inspired by them. The second challenge is feature engineering, which needs domain knowledge in city planning and traffic planning. Luckily, we have experts on board who support us throughout this project. Before proposing our clustering method, I want to show you a few examples of related works in clustering urban areas. In the first one, a cross-section of California with 9 million people is divided into 1,924 tracts. These units are then clustered into 4 classes using census data like population, transportation, economy, etc. In the second example, the city of Strasbourg in France is first divided into 1,000 small spatial units and then clustered into 15 groups based on building types. And lastly, for optimizing the design and the operation of district energy system, a city with 100,000 inhabitants is clustered into 13 groups. These and other related works inspired us to divide Hanau into 500 LGUs. Let's proceed with the data used in this project. Our GPS dataset contains more than 5 million GPS trajectories in the year 2019, which have at least one point in the bounding box surrounding Hanau. These trips represent roughly 2 to 3% of the actual trips, which means we can consider it a representative sample of mobility flows in Hanau. This dataset also contains valuable information about vehicle type, vehicle weight, recording source, etc. Our geodata comes from the OpenStreetMap database. OSM is a free world map that offers the biggest free geodatabase in the world. We extracted most of the information which was available for Hanau, resulting in more than 40,000 points of interest. Using their labels, we categorize POIs into 38 groups, such as residential buildings, sustenance that includes restaurants and bars, education that includes schools and learning institutes, playgrounds, healthcare, financial, and so on. Well, the first step after collecting POIs is dividing the city into smaller units, or in other words, defining LGUs. To do this, we cluster the POIs into 500 groups based only on their locations, that is, their longitude and latitude. Then we define the cluster centroids. After that, we generate Voronoi polygons and clip them to the boundary of Hanau city. The remaining polygons are our LGUs. The advantage of this method is that dense areas are smaller and sparse areas are bigger. If we had divided the city into LGUs with equal areas, we would have ended up with a sparse data set in which many LGUs would have had zero or too few POIs. After defining the LGUs, we establish the variables of the input dataset by counting the POIs of each category for LGUs. As said earlier, we have 38 variables and 500 LGUs. In the right diagram, we see the distribution of total POIs counts per LGU with an average of about 80 POIs per LGU. We start the data pre-processing step with min-max normalization. For every feature, the minimum value of that feature gets transformed into a 0, the maximum value gets transformed into a 1, and every other value gets transformed into a decimal between 0 and 1. We continue with data reduction. The correlation matrix of variables is visualized for a first quick multicollinearity detection. We can see a cluster of 2 variables here in this corner that are highly correlated with each other. We examine that by looking at the variance inflation factor. It is calculated by building an OLS regression for each variable so that it is considered the dependent variable and all other variables are explanatory variables. A VIF value of more than 5 is indicating strong multicollinearity. After aggregating the 3 highly correlated variables, all VIFs are under 5 and we are good to go. Finally, after finding the optimum number of clusters, which is in this case 5, we can cluster the LGUs. In order to interpret the clusters, we use the cluster centroids, which are visualized in the form of a heat map in this diagram. At first sight, the results look plausible. Cluster 0 is the area with the least number of POIs in each category. It represents the green part of the city, which is mostly forest. Cluster 1, 2, and 3 could represent residential areas, but with different characteristics. For example, cluster 1 has very few POIs in each category except for residential buildings. It represents the area which is considered which is consisted mostly of residential building and has very few facilities. Cluster 2 represents residential area which have playgrounds. It has fewer LGUs compared to cluster 1 and they are dispersed among cluster 1 LGUs. Cluster 3 could represent residential areas with schools, healthcare centers, transportation opportunities, and emergency facilities, but few shops, restaurants, or banks. And lastly, Cluster 4 represents the city center with many stores, restaurants, and bars. We continue with city segmentation based on GPS data. The points of interest are, in this case, the origin and destination of private car trips. Each blue point on the map represents a trip start or end point. Same as before, we clustered these POIs into 500 groups based only on their location using k-means. Since the POIs are trips origin and destination points, they are mainly located on streets and parking places. So this time, instead of Voronoi polygons, we build convex hull polygons. This way, we can build relevant segments of the street and parking spots. The parts of the city which has no road network do not belong to any LGUs. We can already see that these parts with no road or parking opportunities are mostly the green part of the city. After generating LGUs, we define variables of the input dataset. In this approach, we want to cluster the LGUs by the hourly pattern of trips origin and destination over the week. We divide the week into three major sections: weekdays, Saturday, and Sunday. Then we count the number of trips origin and destination in each hour of each week section for LGUs. As a result, we end up with 72 variables, which is kind of too many for clustering only 500 objects. So we reduce data dimension using PCA. As can be seen in the right diagram, 95% of the variance in the data can be explained by only 13 components. We use these 13 variables to conduct clustering. By comparing within-class sum of squares and silhouette score for different k's in the k-means algorithm, we find 4 classes to be optimal for this data. Cluster centroids are visualized in this figure. It shows the temporal distribution of trips origin and destination over the week. It can be seen that in almost all LGUs, there is a very low activity between 10 p.m. and 5 a.m. Cluster 2 has the strongest activity in almost all temporal units than Cluster 1 and 0, and Cluster 1 has a stronger activity than Cluster 0. We may also see a positive spatial correlation between mobility activity and the number of POIs from our geodata set. That is, however, a hypothesis that should be investigated further. Cluster 3 is very similar to Cluster 0, but it has a peak between 5 p.m. and 9 p.m. on weekdays. The reason is not deeply investigated, but this may have something to do with the several car dealerships and car repair shops which are located in these LGUs. Well, as a summary, I want to wrap up the crucial points. We use 2 data sources. POIs are derived from GPS data and the open source spatial database of OpenStreetMap. They are used in 2 stages in the process of city segmentation. In the first step, using the only location of POIs, LGUs are defined. In the next step, using the essence of POIs, LGUs are clustered. For example, if a POI is a school, its label is education. If it's a trip origin point, its label is its timestamp. With respect to our use case and context, we can use different POIs with the same approach and get the preferred results for our application. There are still some limitations in our work. For example, consumer car trips are only part of human mobility, and in these models, multiple class assignment is not possible. There is still a large room for improvement. In the future, we plan to try to generate different LGUs and create more complicated clustering models, especially a probabilistic model which allows multiple class assignments. We also intend to integrate fleet mobility data, including trucks, into our models, and also to consider the whole waypoints of the GPS trajectory and not only the origin and destination points. Well, as I said at the beginning of the presentation, these are all the very first results of an ongoing research project. We are still learning and improving our methodology. If you want to keep posted about upcoming results, please take a look at our website at www.relat.de. Thank you for your attention. If you have any questions, please do not hesitate to ask.